So I'm gonna stand off to the side here because I've got to look back at them like in the old days where you have to look back at the slides and use a laser pointer rather than. So go ahead to the next slide. This is just an overview of some of the work that we do in our group because many times there will be criticisms of those who speak at conferences like this that they're not practicing scientists, that they read papers and they write books. But I write very few books. In fact, I've only written one book, and I'll never do that again. And I've written chapters for books, but only at great urging. Usually I just publish papers. We publish papers in journals. That's what we do in my world. And so we work in a number of different areas. And the reason I'm telling you all this is because I want you to see that I really am a practicing scientist. And this is... I rarely attend conferences like this. I'm usually in conferences with scientists and engineers. But we work in an area called laser-induced graphene. That's where we can take, this is a polyimide sheet, and hit it with a laser and write patterns of graphene. Graphene is single sheets of graphite, one atom thick, and it's the strongest material known at that level. And generally it's made at high temperatures, and this is all done in the air with a laser. This is on bread. That's not dropping down ink. That is converting the carbohydrate atoms in the bread, molecules in the bread, these carbon atoms in that bread to graphene. So we convert that. That's a coconut. We turn into a supercapacitor. So we can do it on food. You say, why would you want to write patterns on food? Well, why wouldn't you? So if you have, for example, a potato and you can just mark it very quickly, just as on every one of your plastic bottles, it's a water bottle, it has a little laser scribe date. If we can laser scribe electronics very quickly, you would know exactly what field that potato was picked from, what date it was picked on. And if you build in electronics, you can put an E. coli sensor, a salmonella sensor. You could build in electronics into food very rapidly. We split carbon nanotubes, and we use these in medicine, and we use these also in electronics and batteries. This is two-terminal memory. This has all gone commercial now. This is commercial memory now, two-terminal memory. We work in the area of traumatic brain injury and stroke. There'll be a company launched this year for that, and also dementia. We work on supercapacitors. This is where we've taken asphalt and we can trap over 208% CO2 in it, and we use it for removing CO2 from natural gas. A friend of mine here, Richard, is here, and he works on this as well. So these are areas. So we're real scientists. We do real things. Okay, next slide. And the next slide. This movie's not going to run, so just go to the next slide there. There's Richard there, and let's go to the next slide. That was the research group. So we're going to get into the talk at hand. I'm not going to make any reference to God, any reference to intelligent designer, or anything. I'm just going to allow science to critique the science. What do we have to say about origin of life? What does science tell us? What can we infer here? And so by choice, I am not going to mention God, because if I mention God and Jesus Christ, people will say, oh, Tor introduced the baby Jesus to talk about this. It's not a real talk. All right, this is pure scientific talk. This would work in any medical school, in any chemistry department. Next slide. So this is a cell. What is the origin of life? How do you get a cell like this? What is the origin of something like this? This is an amazing machine. A cell is an amazing machine. It's not just a blob of protoplasm. Every day it gets harder to have the origin of life, to come up with a scenario, because the origin of life becomes more and more complex every day. A cell is a factory. It has the lipid bilayer, which is extremely selective to let certain things in and not other things. It has all of this substructure in here, these little areas where energy is made in here. It has these microtubules which can form, so you can move matter from point A to point B. If you go to a factory, what you see is these overhead hanging machines that are moving materials from point A to point B. in these systems. And the way they do this is they build these racks. But the same thing happens in a cell. You get these microtubules to move material from point A to point B. And then as soon as the material is done moving, the microtubule breaks down and then assembles some other place. You say, well, why doesn't it leave it there? Because then the cell would become too rigid. So it just rebuilds it. It's just amazing factory what's happening in a cell. This is what we have to make. If we want to have origin of life, you got to start here. You don't start here. You start with a single cell. Just build a single cell. That's what we have to do in origin of life. Nobody has ever done this. If you've been taught that simple forms of life have been made, that is a lie that you are believing. Somebody told you a lie. That has never been done. Next slide. Organisms care about life. Molecules don't care. Chemistry, on the contrary, is utterly indifferent to life. Without a biologically derived entity acting upon them, molecules have never been shown to evolve toward life. Never. Molecules don't care about life. They don't know anything about moving toward life. They have no brain. Organisms want to move toward life and keep life going. Molecules don't care about life. Nobody has ever seen molecules assemble toward life. Never. It doesn't happen without a biological entity working on them. I asked all my colleagues, can you show me an example of this? Of molecules moving toward order, moving toward an ordered system where you have a non-regular assembly. Regular assembly is like A, or AB. That you can get pure thermodynamic assembly. But non-ordered assembly is a non-regular pattern. That's what you have in DNA. We know from computer science you have to have non-regular patterns in order to have complexity for living systems. And I asked my colleagues, do you have any example of molecules without a biological entity acting upon them, moving to give an ordered assembly that is a non-regular pattern? And they sent me papers where chemists have taken molecules and assembled them in that way. I said, non-biological entity. You can't have a human doing this. Molecules don't move toward life. Well, even if you want to have molecules move toward life and you have human beings working upon them, can the human beings do it? And the answer is no. Next slide. So, almost every chemical synthesis experiment in origin of life research can be summed up by a protocol analogous to this. They purchase chemicals, generally in high purity, from a chemical company. All right, so that's what they do. They first purchase the chemicals. They mix those chemicals together in water in high concentrations in a specific order under some set of carefully devised conditions in a modern lab. Then they can obtain a mixture of compounds that have a resemblance to one or more of the basic 4 classes of chemicals needed for life. So what you need for life is you need carbohydrates, nucleic acids, amino acids, and lipids. That's what we know. All life we know composes those 4 building blocks. So they try to make those 4 building blocks. Then they publish a paper making bold assertions about origin of life from these functionless crude mixtures of stereochemically scrambled intermediates, much like Miller did in 1952. Nothing has changed in 66 years. Nothing. Nothing's changed. Exactly where we were in 1952 is exactly where we have remained. Think about what's been done in science in the past 60 years. Think about how we have now satellite connectivity. Remember, in 1952, there had never been a satellite. Now we have satellite connectivity. We have cell phones. We have structure of DNA. We can manipulate DNA structure. Nothing has changed in origin of life studies in 66 years. That's important to realize. Then you engage with the ever gullible press to dial up the knob of unjustified extrapolations. Watch the mesmerized layperson exclaim, "You see, scientists understand how life formed." Then you encourage a generation of science textbook writers to make colorful, deceptive cartoons of raw chemicals assembling from cells which then emerge as slithering creatures from a prehistoric pond. That is exactly what is done every one of their experiments. It's all done like this. Every one of their experiments can be fit into this. And so what's going to happen is I'm going to go back and a bunch of you are going to send me articles. Look at this. These people have made life, haven't they? It fits into this. Trust me, it fits into this. Every one of them. Next slide. So, here's the synthesis problem. If you just want to make the molecules, remember we have to make those 4 classes of molecules. If you just want to make the molecules, here's what you got to do. Molecules that compose living systems almost always show homochirality, meaning that they have they have one-handedness and not the other. The vast majority of biological molecules, except for very small ones like water and acetic acid, anything larger than that, they're mirror images. Just like your left hand and your right hand are mirror images. They're non-superimposable. You can't put a left-handed glove on your right hand. It doesn't fit. All molecules are like that in biology. That is hard to make. It is very hard to make just one mirror image of a compound. It can be done, but it's very hard. So that's part of the problem. When you're building molecular systems, constant redesigns are needed to take the synthesis back to step one. So that take the synthesis back to step one. So in other words, when you're going and you're making something, you're like, oh boy, those conditions didn't work. My stuff decomposed. So you go back to step one and you bring through more starting material. And so you take small amounts. You try this, you try this. Anything that would be happening in a prebiotic earth, it's marching along trying to make something. If it makes a mistake, you can't pull that entity off. Very hard to pull the entity off. Once it's on there, it's on there. So you've been going along, say, for 400 million years, if you want to take these sorts of numbers, and all of a sudden it's put a wrong moiety on there. Uh-oh, what am I going to do? Well, you got to go back to step one. I got to go back 400 million years? Yeah, you got to go back there. Well, I don't know how to go back. Well, why not? Because I never kept a laboratory notebook. When you don't keep a record of it, you don't even know how to go back. You don't even know what you're going toward. Because it doesn't know that it's moving toward life. Remember, molecules have no brain. They don't know where they're going. That's the synthesis problem. And they don't know how to stop the course of progression or why to stop. There's no target. They don't know, I think we'll form life today. I think we'll make a certain cell. You don't know that. Molecules don't know that. So they're going along and chemical reactions are happening. It doesn't have a target. When you're in the lab, you're going toward a particular target. You know where you're headed. Here it doesn't know when to stop or how to stop. Maybe it's made a carbohydrate. It doesn't say, well, I made a carbohydrate. I think I'll stop synthesizing. No, it'll go on and make something else from that. It doesn't know how to stop. Time, although claimed to be the great savior of abiogenesis, that's before there's biology, abiogenesis can actually be the enemy. For example, carbohydrates are kinetic products. They undergo caramelization or the Cannizzaro reaction. They decompose. So in other words, when you make a carbohydrate, that is not the final product that would form in that reaction mixture. You have to stop the reaction. So a chemist watches the reaction and they stop it at a certain time to stop that progression of the molecule going on. If this is just undirected, unguided, it keeps going to other garbage. Carbohydrates are kinetic products, meaning that they caramelize, they polymerize into a bunch of trash. Just like when you take sugar and you heat the thing up on the oven and the thing turns into caramel, that's what happens to carbohydrates. They don't stay nice, simple carbohydrates. They end up actually dehydrating. A prebiotic system doesn't have the ability to easily purify the structures. You have to be able to purify, because if you cannot purify, then the byproducts build up in the system and they start using up your starting material and they start inhibiting the reactions that you want. You have to be able to do purification. Without purification, you can't work. Every chemist has to run a reaction, then you stop, you purify, you get it pure, and you go on the next step. Once in a while, if it's a really pure reaction, you can go on one or two steps, but you have to purify. Reagent order is essential, reagent addition order. You can't just say all the reagents mixed together and you get what you got. You're making a cake, you got your flour, you got your milk, you got your eggs. You say, well, I think I'll just add the frosting now. No, there's an order to this. This is real. This is what you do in chemistry. Things have to be added at certain times. You can't just add it whenever you want to. Reagent addition order at proper timing is critical. The parameters for temperature, pressure, solvent, light, no light, pH, atmospheric gases have to be carefully controlled in order to build complex molecular structure. There's no way around it. This is what's needed. You have to have characterization at each step. This is hard to do. Chemists have to characterize things at each step because you have to make sure what you've got before you can go on to the next step. How does nature characterize? Well, right now, biological systems characterize things by every time it makes something, there's an enzyme that checks that structure. If it's not the right structure, there are other enzymes that come and chop that up into smaller pieces and try rebuilding it again. You get a mistake in the DNA. You have enzymes that run up and down the DNA, find this mistake, excise it, and then stick in the right base there. But in a pre-biological world, there are no enzymes. How does it check it? And every time, whatever it's using to check it, whatever system is needed to check it is more complex than the system that it's checking. So where'd you get that from? Nobody knows. Everybody's clueless on this, but nobody wants to admit it. There's the mass transfer problem. This seems like not a problem to you, but let me tell you something. This is the killer of it all. Are there any synthetic organic chemists in here? Any synthetic chemists here? Any synthetic chemists? Get your hand up high. One there. Okay. So and one there. Okay. If I say something that's not true, I want you to stand up and just say liar. All right? If I say something that's not true, just stand up. All right? Because I want these people to know, for all they know, I'm lying. You have to verify on this. All right, the mass transfer problem. Anybody who's done complex organic synthesis, what you do is you start with like a half a kilo of material, and you go along, and your yields are never 100%. You're purifying, you're going, and you end up with 2 milligrams, and you're not at your target yet. So what do? Then you go back to the beginning, and you make more, and you follow the defined route that you had defined before, and so now you can keep your yields higher, but you keep having to go back and pull up starting material from the rear. You're bringing up more material. How do you do that? So say in nature they started, say somehow it started and it got a kilo of formaldehyde and acetone, and it's going to start combining these. So these are going to go along and start reacting. At some point it's going to run out of material. How do you go back to the beginning and get more? Again, you never kept a laboratory notebook, so you never know how you got there. So even if you could repeat it, go down the same junky path and you'd run out again. You'd never get to where you want to go. Nature keeps no laboratory notebook. Next slide. So this is just the motor part on the nano machines. We were building nano cars. We actually won in 2017 the International Nano Car Race. It was the first race. We went 150 nanometers in an hour and a half. And that sounds like a long time to go 150 nanometers, but we actually the second place people behind us were the Swiss team. Took them 5 hours beyond us. So it took them 6.5 hours total. And none of the other international teams were able to complete the race in 30 hours. So it's not easy to go 150 nanometers when you're driving these little cars. But anyway, so this is the motor on just the car. And so you see these different steps. You reacted at all these different temperatures. Here, you have to have it at 5 degrees, then cool it to minus 10 and minus 15, and then minus 50 degrees here. And then you run these reactions. This one's done at 130 degrees. This one's done at 60 degrees. You're like, what's with the temperature? What's your problem? Why you're cold, hot? Why do you do this? Oh, because we just like to. We just like to cool things down and heat things. No, you have to. Each step needs its own parameters. How does nature know that? You say, well, it was, it's some deep sea vent. Okay. So it warmed up there. And then what? And then it left the vent. And then it, ended up at some other really cold place. And then it went back. And then it went back and back and forth. Nobody knows how any of this ever happened in nature. Nobody knows. Next slide. So this is the experimental procedure. So what you do, you take an oven-dried 3-neck round bottom flask, and you charge it with 33. You add magnesium sulfate and dichloromethane, and you cool it down here, cool it down. This is just one step on that thing. And then you get the yield. This is just one step. There's all these things you got to do. You have to know what you're doing. Even if I just gave this to you, you wouldn't know what to do. So you have to be an experienced chemist to take this and to be able to repeat this. So what is a mindless abiological system? What does it know how to do? Nobody knows. Next slide. Then you have to characterize it. Once you make what you want, you have to characterize this. We have this tool called NMR, and you get these peaks. And from these peaks, you assign the structure so you can get the exact structure. This is how all the pharmaceuticals that you take, this is how the structures are assigned. You run these spectra. And you say, well, nature doesn't have to do this. It doesn't. Nature uses a more complex system. It has a different glove for every hand in nature, a different enzyme that detects structure problems. It's more complex than this. This is a general tool. But the next slide shows us how, next slide, this is what we have to write to convince our colleagues that we got what we thought we got. A combination of standard deuterium, proton, C13, depth 135, C13 experiments with standard 2D, H1 cozy, H1 NOE, boom, boom, boom. So you go all through this. Not done. Next slide. So that's part two. All of that needed to just characterize the one molecule. Characterization is harder than synthesis. It really is. Any chemist will tell you. You can make something, but it takes you a lot longer to characterize. And you have to know the structure because you have to know what to do for the next step. Nature is confronted with the same thing all the time. Making molecules is hard. Next slide. This paper had 281 pages of supplemental characterization data. I showed you a paragraph of characterization. 281 pages of that to convince the world that we made what we were making when we made those light-driven motorized nanocars. How does a dumb, abiological world ever do this? Nobody knows. They're all clueless, but scientists aren't saying how hard it is. Next slide. This was the first generation motor that we put in the car. It worked, but it only rotated at 1.8 revolutions per hour. When we rebuild it without that sulfur atom there, then that 5-member ring, then it goes 3 million rotations per second. All right, so small changes can make a big difference. Well, what do you do? Well, what you do is you just come here and you erase that sulfur and you do that. Now that you can do on a blackboard. But this took us back to step one. This is what I'm talking about. When something, you're going along and you want to build and you say, oh, I'm just near life. If you have one thing wrong, it doesn't work. So, well, you just modify this and it'll work. All right, go back to the beginning. Go back 1 billion years to the beginning. It's too hard. Nobody knows how this thing is solved. You can't build the molecules. Next slide. And then, so remember, these just to make the molecules, the simple molecules. You got to have the carbohydrates, you have to have the lipids, you have to have the nucleic acids, you have to have the proteins. Even if you make an amino acid, how do you hook the amino acids together? Amino acids don't hook together by themselves. We're not even talking about order. How do you just get them to hook? I mean, somebody sent me a paper just last night. I mean, here's a paper just came out on self-folding molecules.